Now let's take and move away from vectors to matrices and see what are some common operations that we can do on matrices. One of the things that we typically widely used is the matrix addition operation. And here it is only valid for the matrices which have same dimensions, and you can add them together to create a third matrix which is also of the same dimension as the first two matrices. And the idea is like you are adding these two matrices by adding the corresponding element together. Okay, so let's see how this might look like. First thing to note, we have matrix A and matrix B. The number of rows of matrix A is equal to the number of rows in matrix B, and the number of column, which is 2 here, is also equal to number of column in matrix B. So they are of the same dimension, and then the matrix operation is valid. I can add them together and call the resultant matrix as X. And how this operation is carried out? Essentially, I have 2, right? I take the first element of the 1 1 element of the A matrix and 1 1 element of the B matrix. I add them together, and that becomes the 1 1 element of X matrix, right? Similarly, I can take this 1 and this 10 and I add them at the corresponding location. And similarly, I can take all the corresponding elements and sum them together, and we will get this resultant matrix X, which essentially implements the matrix addition that we are interested. So if we simplify this, the overall matrix X, which is coming and derived after adding two matrices A plus B, is given by this matrix X that we have. So this is the simplest way to understand matrices. The second important operations with matrices is that we can transpose them. Okay, and transpose turns out is defined for matrix of any size. Okay, and what it essentially does, it flips the elements along the main diagonal, and you will see that in a sense it is essentially inverting the rows and column of a given matrix. And this operation is denoted by superscript capital T next to the matrix. So if I have matrix, let's say M, and I'm taking a transpose of this one, right, then this transpose will be denoted by this M superscript T, right, and this will be denoting the transpose of given matrix. Okay, what we see is like the columns of M transpose are essentially the rows of M. That is what this operation means. So let's take an example problem and let's see how we can determine or derive of the transpose of a given matrix. Okay, so let's take a matrix which is given here, and if we want to take the transpose of this matrix, one thing that I want you to notice is you will see this matrix has first column which is 2, 5, minus 2. So this is going to become the row of M transpose. So the row will have 3 elements. This will be 2, 5, minus 2. Now the second column of the matrix M is going to become the second row of the transpose matrix. So let's see how this looks like. So if I'm doing this transpose, I'm taking this row, so this column of the matrix, and I'm converting that into row. I'm taking this column and converting that into this row. And this is what the transpose is. Now, one thing to note is like, the dimension of M is 3 cross 2, 3 rows and 2 columns. When we are taking transpose, it becomes, essentially 2 rows and 3 columns, right? So the dimension also gets changed during the transpose operations that we have. Okay. So this is a simple example of how to take transpose of a given matrix. Okay. The operation has no effect if the matrix is symmetrical. So the matrix is symmetrical, and if you transpose them, both the matrices are going to be same. Okay. Now that brings us to the third operation that we can do on matrices, which is known as the trace. Okay. The trace of a matrix is defined by this trace in the round parenthesis M, and is essentially the sum of the diagonal element of a matrix. So whenever you have a matrix, find out what are the diagonal elements of the matrix, sum them together, and once you sum them together, you essentially arrived at the trace of that matrix that we have. Okay. So let's take an example problem and understand how to compute the trace of a given matrix. Okay. So let's say we have this matrix defined here, right? What are the diagonal elements? So the diagonal elements are this, 3 elements right here. I will take all those three elements, which is 5, minus 6, and 8, and I will sum them together, and that essentially will give me the trace of the matrix M. So let's see how that will be done. So trace of M will be 5 minus 6 plus 8. If I simplify that, I will get 7. So the trace of this matrix is essentially going to be 7. And that is what is meant by a trace of a given matrix. Okay. Now trace operators have some useful properties. So trace of a matrix M is also equivalent to the trace of M transpose. And if you assume the same matrix shape and the order of inverting columns or columns into row and changing them to create a new matrix, it's not going to change the trace. Okay. Now one of the most useful thing about trace is it is one way to compute what is known as matrices of Frobenius norm. And Frobenius norms comes into computations in machine learning algorithms later on, and so it's important for us to know how the trace is useful in computing the Frobenius norm of a matrix. Now, if you want to compute the Frobenius norm of a given matrix, first thing that you need to do is you take that matrix M. Let's say if you want to compute the Frobenius norm of M, you take the matrix M, and then you take the transpose of that matrix and multiply them together. So what we are doing, we are taking M, we are transposing M, which gives me M transpose, and then we are multiplying them together. So these two matrices are first multiplied. The matrix M itself with the transpose of it itself is multiplied, and when we take the transpose of that multiplied matrix and take a square root of that, that will give me the Frobenius norm of the original matrix M that we are interested. Okay, so this formula where we are basically taking the transpose of M multiplied by M transpose itself and taking a square root of all the entries, it helps us in computing the Frobenius norm of a given matrix. Okay, this is important to keep in mind because this is typically a formula that is used in the computation of the Frobenius norm, which is one of the important ways to use the traces in computations we are interested in.